Okay, so let us start today's session. Today we start from experimental methods calculate order or rate law of reaction. So there are different methods. First is initial rate law method. So in initial rate law method, let us say we have a reaction in which A moles of A react with B moles of B and C moles of C give product, and rate is K, A raised to power X, B raised to power Y and C raised to power Z. So now order of reaction is X plus Y plus Z. So we can calculate X, Y and Z from the experimental method. Let us say we do 4 experiments. An initial concentration of A, B and C, they are changing, and accordingly initial rate is also changing. So first of all, from experiment 1 and 2, experiment 1 and 2, see there is a change in concentration of A, but concentration of B and C be left unchanged. There is a change in concentration of A only. So when we write the expression, rate law expressions R1 and R2, there is a change in concentration of A only. So R1 by R2 becomes equal to A1 by A2 raised to power X. This way X can be calculated. Now if we consider A experiment 1 and experiment 3, see there is a change in concentration of B only. So from here we can calculate Y, and from experiment 2 and 4, see A is same, B is same, there is a change in concentration of C only. So we can calculate Z. In this way we can calculate order of reaction with respect to A, B and C, and overall order of reaction becomes X plus Y plus. Second is half-life method. So you know what half-life and initial concentration, there is an inverse relation, A raised to power n minus 1. So from this half-life method can be applied for the reactions if there is one reactant only, A, two products, or if there are different reactants, then their concentration should be in the stoichiometric ratio. Like see, 2A react with 3B, so concentration of A is 2A and concentration of B is 3A according to the stoichiometric ratio. From here we can calculate half-lives. You know half-life, let us say 1. If initial concentration is A1, half-life 2 for the same reaction if initial concentration is A2. So from here half-life 1 upon half-life 2 is equal to A2 by A1 raised to power n minus, and taking log on both sides, log of T half 1 by T half 2 equal to log of A2 by A1 raised to power n minus 1, and that implies it is n minus 1 into log of A2 by A1. N minus 1 is equal to log of T half 1 minus log of T half 2 divided by log of A2 by A1, A2 minus log A1, and in this way n comes out to be 1 plus log of half 1 minus log of T half 2 divided by log of A2 minus log of A1. So from the half-life periods given, we can calculate order of reaction. So only 2 readings are sufficient, but if there are more readings, then that is used to ensure experimental errors we can minimize. So more number of reading means we are minimizing the experimental errors. Now using integrated rate law method. So in integrated rate law method, we should have data according to that at time 0 concentration is C naught, at time T1 concentration is C1, C2, according to the different times. So now what we do, we write integrated rate law expressions. You know what is K for zero order reaction? It is C naught minus Ct by T. So what we do, we write at different times we will calculate K by fitting the data in this. If K comes out to be same for zero order reaction, then means it is a zero order reaction. If it is not equal, they are not almost same, then we shift to next, that is first order reaction. So according to first order reaction, K is equal to 1 upon T natural log of C naught by Ct. So if we put values of C naught and Ct at different time intervals and K comes out to be same, that means it is first order reaction. If it is not so, we will go to the next, that is K equal to 1 upon K equal to 1 upon T 1 upon T minus 1 upon T naught. So it is expression for second order reaction. So in this way, by using hit and trial method, we can calculate values of, we can predict the order of the reaction, and it is a hit and trial method. So it is most time consuming method, so we will not prefer this method. But if data is like this, we can use integrated rate law. Now Ostwald's isolation method. So in Ostwald isolation method, what we do, we isolate reactants and we change the concentration of the others. For example, case 1, let us calculate rate order of reaction with respect to A. What we do, we take concentration of B and C in excess. That means if B and C are in excess, their concentration is almost same. So rate is A dash into A raised to power x, and accordingly we will calculate value of x just like in initial rate law method. Case 2, what we do, we take A and C in excess. A and C are in excess, rate is A double dash B raised to power y. We calculate y from this expression, and in case 3 we take EC, AC and A and B are in excess. So if A and B are in excess, so rate is equal to K, let us say triple dash C raised to power C. So in first case, we will change the concentration of A and we calculate concentration of B and C the rate of the reaction, and we calculate Y. In Third case, we will change the concentration of C, and from the rate law we calculate the value of, and in this way calculate order of reaction with respect to A, B and C, and overall order of the reaction is X plus Y plus. So this is the question for you. For the reaction A plus B to give C, the experiments were performed in the presence of large amount of B. Measure the initial rate, that is BF, as a function of initial concentration of A. That means BF is proportional to initial concentration of A, let us say raised to power X, because we have to calculate order of reaction with respect to A. So see, VF is equal to some constant K, that is rate constant, A naught raised to power X. So taking log, because graph is log of F versus log of A naught. Log of VF is equal to log of K plus X into log of A naught, right? So we have to calculate value of X, that is the order of reaction. Could you do it? Do it fast. What is the order of reaction? That is the value of X. Graph is given, log F versus log A naught. You will get two equations, and from those two means quadratic equations, linear equations. It is just like linear algebra. So see, first of all, this value, this is 7, and this side it is value 6. Is 6 and 7, right? So first equation is 7 equal to log K plus 6x. That implies 7 minus 6x equal to log K, right? Second equation, see, is 11. On the other side it is 12. So 11 equal to log K plus 12x. That implies 11 minus 12x equal to log K. So means 7 minus 6x equal to 11 minus 12x minus 6x plus 12x equal to 11 minus 7. That means 6x equal to 6 x comes out to be 1. Is A option is correct. Seven minus 7. So it is 6, x equal to 5. Okay, got it. It is 2 by 3, right. It is option C. Okay, sorry beta. It is C option is correct. Have you done like this only, or you have? Okay, that's also. What about others? Understood? Okay, now how do we progress? How do we monitor the progress of the reaction? So if there are gaseous reactions, that case we will either measure pressure and volume. Either we see the progress of the reaction by pressure measurements or by the volume measurements. If we see the pressure measurements, then we keep volume and temperature constant. If we see the volume measurements, we will keep the pressure and temperature constant. And you know, pressure or temperature, volume, both are directly proportional to number of gaseous moles. Keep in mind, we will take into account only gaseous moles. We are not taking into account the number of moles of the liquid or solid. So method is applicable like this. If we have An gas to give Na gas, 1 mole of gas composed into N moles. Should be a change in gaseous moles. Like in the second case, N2O4 to give 2NO2 gas. 1 mole changes into 2 moles. 2 moles into 4 moles. There are 2 moles into 7 moles. In this way, see, A solid to B gas plus 2C gas, or A aqueous give 2B gas plus C gas. If reactions are like this, we can calculate either pressure or volume, and by making use of those pressures or volumes, can calculate rate constant. Let us say we have data either in pressure terms. So pressure is given at 0 time or and at the same time at infinite time and at different time intervals. Same if volume is there, volume is given at 0 time, given V2 and at infinite time. So we will use the relation for volume as 1 upon T natural log of V infinity minus V naught divided by V infinity minus Vt. If pressure is there, K equal to 1 upon T natural log of V infinity minus P naught divided by P infinity minus naught. And if we have optically active compounds, then we use relation as rotation, specific rotation at infinite time minus specific rotation at 0 time divided by infinity minus specific rotation at time t. Now, if let us say T infinity is not given or T infinity is not given, that means at infinite time it turns into 0. We take it as 0. If it is not given, we take this value as 0. So that means this equation is modified as k equal to 1 upon t natural log of p naught by vt, or k equal to 1 upon t natural log of p naught by pt. So whatever is not given, just take it as 0. Like if this one of the case, these are general expressions, okay? These three are general expressions. Let us say if p infinity or p infinity is not given. That we have done. If p naught or p naught is not given, that means initially it is 0. Take it as 0. So k comes out to be 1 upon t natural log of p infinity divided by p infinity minus v, or is equal to 1 upon t natural log of p infinity divided by p infinity minus pt. Let us say this is the reaction. For the reaction an gas, if an a gas and values are given, see at 0 time p naught, at t1 time is p1, at t2 time it is p2, at infinite time it is p and p naught. So let us apply the formula. If you remember, k equal to 1 upon t natural log of, what's the formula? P infinity minus naught divided by p infinity minus pt. So just put the values. Natural log p infinity is n p naught minus p naught divided by, again p infinity n p naught minus pt, either pt p1 or p2. If time is t1, it is p1, time t2 it is t2. So that implies comes out to be 1 upon t natural log of n minus 1 p naught divided by n p naught minus pt. See, let us say this is the expression. If we do by solving it, then see at time t, let us say x mole are decomposed, are converted into product. So p naught minus x gives nx. So what is total pressure? Here p total is total pressure. Total pressure is equal to p naught minus x, the reactant, and nx from the product. So now from here x comes out to be n minus 1 into x equal to pt minus p naught. X is equal to pt minus p naught by n minus 1. X is equal to pt minus p naught upon n minus 1. Here pt is equal to, pt means concentration after time t, that is proportional to P naught minus X. So concentration after time T, that is P naught minus X, the value of X, Pt comes out to be N into P naught minus Pt upon N minus 1. So K comes out to be 1 upon T natural log of P naught into N minus 1 divided by N P naught minus T. Okay, do this question. Progress of the reaction, NH4NO2 aqueous to 2HO liquid, 2H2O liquid plus N2 gas. The total pressure measurement are given. Total pressure at 0 time is P naught is 50 mm of Hg. After time 20 means P20 is given. mm of Hg, and P infinity is also given, is 90 mm of Hg. What is K? Or calculate half life. Yes, better. K is one upon T natural log of P infinity minus P naught divided by P infinity minus Pt. Yes. Are you trying? 10 minutes. It is 1 upon 20 natural log of what is P infinity, 90 minus 50 divided by 90 minus 80, 1 by 20 natural log of 40 by 10. It is natural log of 4. So it is 1 by 10 natural log of 2. Right? So you know what is half-life? It is natural log of 2 by k. This way, you know, natural log of 2 by k equal to 10. Expression comes out to be 10 minutes. 8. See, at time 0, initial constant, take it as a. After time t, let us say it is a minus x, and after infinite time it is 0, and the concentration of nitrogen gas becomes a. So a is proportional to 90 minus 50, and x is proportional to 80 minus 50. That means a minus x is 10. This way, log of 2 by e half comes out to be 10 minutes. Next, same expression, but this time instead of pressure, if volume is given to us. See, again there is V naught, V infinity, and the other volumes. So obviously K comes out to be 1 upon T natural log of V infinity minus V naught upon T. This expression keep in mind, because MCQs there is no need to derive it as a whole, but X is proportional to Vt minus V, and A is minus V. That is expression V infinity minus V naught, and X is equal to Vt minus naught. A is equal to 1 upon T natural log of A upon A minus X, and A is V infinity minus V naught, and A minus X is V infinity minus T. Okay, acid catalyzed hydrolysis of ester, that is ethyl acetate plus H2O, the presence of acidic medium, that is HCl, we get acetic acid and ethanol. Progress of this reaction is measured by titrating the reaction with sodium hydroxide. So sodium hydroxide consumed initially is V naught. Tell me, initially ethyl acetate is not hydrolyzed at all. So where this V naught will be used? It is used to initially, yes, it is used to neutralize HCl. So A, let us say concentration of ethyl acetate, initially it is A, and acetic acid and so after time t is A minus X, so acetic acid is X, and at time infinity, whole of the ethyl acetate is used up, becomes 0, and acetic acid now it is A. So initially, why we do not consider ethanol? Because sodium hydroxide utilize only acids. Sodium hydroxide is a base, so it utilize HCl and acetic acid. It is used up or consumed to neutralize HCl and acetic. So initially acid present is catalyst. HCl, that is proportional to initial concentration used up, that is V naught. Now after time t, dt, volume used of NaOH is HCl plus amount of ethyl acetate, amount of acetic acid formed after time, L plus X, and at infinite time L plus A, that is to B infinity. And in this way can use this expression, that is 1 upon T, again same expression, natural log of V infinity minus V naught upon V infinity minus T, that is T. X is proportional to dt x is A. A is proportional to E infinity minus V naught. X is proportional to dt minus V naught. A is proportional to T minus V naught. A minus X to A is E infinity minus V naught minus E minus V. This way A minus X to infinity minus, so K is 1 upon T, natural log of A upon A minus X. A is proportional to infinity minus V naught, and A minus X is minus, okay, hydrolysis of cane sugar, or call it as inversion of cane sugar. Can you tell me why it is called inversion of cane sugar? Yes, very. The sucrose is dextrorotatory and glucose is dextrorotatory, fructose is levorotatory, and levo-rotation of fructose is greater than dextrorotation of glucose. Overall, when it is hydrolyzed, dextrorotatory sucrose is converted into levorotatory mixture of glucose and fructose, and that's why this mixture is also called as invert sugar. Okay, so let us say we measure this progress of the reaction because they are optically active. So we measure by the plane for the light, that is at time 0. Let us say its initial specific rotation is theta naught. After time t1, t2 it is theta 1, theta 2, and at infinite time it is theta infinity. When time is 0 means initially only sucrose is present. Its concentration, let us take it as small a, glucose and fructose is 0. After time t, glucose is a minus x, glucose and fructose x, because one sucrose will give 1 mole of glucose and 1 mole of. So after finite time, when reaction is complete, it becomes 0. Glucose is not there, but glucose and fructose A and No, A divided by A minus X, that is equal to theta minus theta naught, theta infinity minus theta naught divided by theta infinity. That is same expression we can. Okay, this is the question for you. Hydrolysis of sucrose in excess of acid solution follows first order kinetics. That you know, it is a pseudo first order reaction and results in D-glucose and D-fructose. Since sucrose, D-glucose and D-fructose, they are optically active compounds, so the progress of the reaction can be monitored by measuring the angle of rotation of the polarized light in a polarimeter at different times. In certain experiment, 1 liter of 0.1 molar sucrose solution is hydrolyzed and angle of rotations are given. See, R naught is given to you. Know the formula, you can easily calculate it. R infinity is given to you, minus 53, and R at time 30 minutes given 5 degree. These are the angles of rotation. At times 0, that is R naught, at time finite, that is R infinity, and at after 30 minutes. We have to calculate, and the concentration of sucrose at time t, that is proportional to change in the angle of rotation, that you know, RT minus R infinity. So molecular mass of sucrose is also given, so we have to predict which statements are correct. Half-life of the reaction is 15 minutes, or rate constant is 3.85 into 10 raised per minus 4 per second. Mass of the sucrose hydrolyzed in 60 minutes, 25.6 gram, or rate of the reaction at 30 minutes, 1.925 to 10 raised per minus 5 molar per second. Yes, beta. I will give you a hint. First of all, calculate K. Calculate K, have this formula, 1 upon T natural log of theta infinity minus theta naught divided by theta infinity minus theta t. Here it is R. You can take it as R infinity minus R naught, theta infinity minus theta t. R infinity minus R naught divided by R infinity minus R 30. His time is 30. Let's first calculate K. But keep in mind the rate constant is given per second, but the time we have in seconds. So calculate it in per second, we will multiply it by 60. It is in per minute, right? Calculate in per second, it is 30 into 60 natural log of R infinity minus R naught divided by R infinity minus R 30. And mass of X hydrolyzed, that is X actually. Rate of the reaction after 30 minutes. So after 30 minutes, rate is equal to K into concentration of hydrolysis after 30 minutes. I think these are the enough hints that you can solve it. More than one statements are correct. Are you trying or here K comes out to be 1 by a natural log of R infinity is minus 15 and R naught is minus R naught is 55 divided by minus 15 minus RT. In this way, K is equal to 1 by 30 natural log of 40 by 20. That implies it is 1 by 30 into natural log of 2. So from here it is 0.93 by 30 per minute. But to calculate K in per second, it is 0.693 divided by 30 into 60. Comes out to be 3.85 into 10 raised to power minus 4. At the same time, from here see, natural log of 2 upon K is 30. That means half life is 30 minutes. Because natural log of 2 upon K is T half. So half life is 30 minutes. From here, the rate of reaction after 30 minutes, it is given that shows is 0.1 mole per liter. So after 30 minutes, it becomes half 0.05 molar. And after 60 minutes, it becomes 0.025 molar, because it is first order kinetics. So after every 30 minutes, it is halved. That means first option is incorrect, because half life is 15 minutes, it is actually 30 minutes. Now rate of reaction at 30 minutes. So rate of reaction after 30 minutes is K into concentration of sucrose after 30 minutes. K is 3.85 into 10 raised per minus 4 into 0.05. What is the value? On 1.925 into 10 raised per minus 5. That means last option is correct. And mass of the sucrose hydrolyzed in 60 minutes. See, sucrose left after 60 minutes is 0.025. So how much amount is hydrolyzed? Sucrose hydrolyzed is 0.075 mole, because it is 0.075 molar that is hydrolyzed. So amount hydrolyzed is multiplied by 342.3. So 0.075 into 342.3, it comes out to be it is round about 25.6, I think. Is it true? That means option A, that is incorrect. E, C, D. Other three options are correct. Done? Understood? Next is 2A plus 3C to E plus 5D. Initially, A pressure is not, or E pressure is 1. E and D, they are 0, 0 initially, and rate depends on A only. First, it follows first order kinetics. And calculate the rate constant of the reaction in terms of P naught, P1 and T. See, we have 2A plus 3C give 2, this is actually 2A plus 3B to give P plus 5D. Initially it is P naught, P1, 0, 0. So after time T, let us say X moles are decreased. So let us take it as 2X, 3X becomes 2X and 5X. Because if 2 moles of A react, then it will react with 3 moles of B to give moles of C and 5 moles of T. This way, P naught minus 2X, or if you take it as X, and then you can do it. If you take it as X, then it becomes Px by 2, it becomes X, and it is 5 by 2X. Both give same results. Total pressure becomes P naught minus X plus P1 minus 3X by 2 plus X plus 5 by 2X. So it comes out to be P naught plus P1 plus X that implies X is equal to Pt minus P naught minus P1. It is P naught. A is proportional to P naught, X is proportional to Pt minus P naught minus P1. This way, A minus X is two P naught minus P. A minus X is equal to P naught minus Pt plus P naught plus P1. That implies A minus X proportional to 2 P naught plus P1 minus Pt. So A and A minus X we have, so we can calculate the rate constant. See, rate constant comes out to be 1 upon T natural log of A upon A minus X, that is P1 plus 2 P naught minus Pt. Dependence of rate of reaction on temperature. So, you know, after increasing temperature by 10 degrees Celsius, rate of reaction is almost doubled or sometimes tripled, and that is called temperature coefficient. That is rate of the reaction or rate constant after time plus 10 divided by rate of reaction or rate constant after time T. That is called temperature coefficient, and is generally between 2 and 3. So if let us say temperature coefficient is 2, then the rate of reaction after time T plus delta T equal to temperature coefficient raised to power delta T by 10. Let us say rate of reaction at 20 degrees Celsius is R. What is the rate of reaction after at 60 degrees Celsius? So rate of reaction at 60 degrees Celsius is equal to 16R. How do we calculate? R60 is equal to RT, that is R. Temperature coefficient is 2 raised to power T minus 20 divided by 10. That is R 2 raised to power 4. This weight is 16R. Again, if R dash is rate constant at 20 degrees Celsius, calculate rate at 45 degrees Celsius. Again, we subtract 45 from 20, that is 25 divided by 10, that is 0.5. R dash is equal to R into 2 raised to power 2.5, that is 4 under root 2 R. This is energy profile diagram, and this is for endothermic reaction or exothermic? Is for exothermic reaction. This is energy of the reactant, energy of the product, and this is activation energy of the forward reaction, energy for the backward reaction, and this is transition state. From 0 to transition state, the total energy is called threshold energy. It is the minimum amount of total energy required to carry out a reaction. And from here, this is the minimum kinetic energy of the reactant is required to carry out the reaction. And enthalpy of the reaction is enthalpy of the product minus enthalpy of the reactant, or is also equal to activation energy of the forward reaction minus activation energy of the backward reaction. And from Maxwellian distribution, what is this A e raised to power minus EA by RT? The fraction of the molecules is energy greater than EA. This part is e raised to power minus EA by RT1, and we take into account whole is e raised to power minus A by RT2 is the fraction of the molecules, the energy greater than or equal to E. Having kinetic energy equal to or greater than EA, that is e raised to power minus EA by RT. And what is A? A is called free exponential factor or Arrhenius factor or frequency factor, and it represents collisions taking place proper orientation, that is A, that is the maximum rate. A is also called maximum value of rate constant. It is the maximum value of the rate constant. And A and EA, they are independent of temperature generally, and activation energy and threshold energy that I took. So if we plot a graph or see this relation K into e raised to power minus A by RT, we plot a graph between natural log of K versus 1 upon T. Graph is straight line, slope minus EA by R, and intercept natural log of A, and activation energy is always greater than or equal to 0. It can never be negative. When temperature tends to infinity, then K becomes equal to A, that is the maximum rate, maximum value of the rate constant. So if we have two different temperatures T1 and T2, the relation natural log of K2 by K1 equal to activation energy by R to 1 upon 1 minus 1 upon E. If we have reversible reactions, so you know, for the forward rate constant, values like this: forward Arrhenius constant in e raised to power minus activation energy for the forward reaction upon RT. For the backward reaction, it is AB is e raised to power minus AB by RT. So equilibrium constant is always equal to forward rate constant divided by backward rate constant. Hello. So AF into e raised to power minus EF by RT, AB e raised to power minus EAB by RT, and you know AF by AB e raised to power, I told you earlier, LP of the reaction is activation energy for the forward reaction minus activation energy for the backward reaction. So that means equilibrium constant is related to enthalpy of the reaction. If enthalpy of the reaction is negative, that means if delta H is positive, means for endothermic reaction. So whenever 1 upon T increases, you know, value of natural log of K equilibrium decreases. It is like this. But if delta H is negative, so negative becomes positive. So see the graph. Natural log of K equilibrium versus 1 upon T for exothermic reaction, it goes upward. Slope is positive because you know this slope is minus delta H by R, and delta H is negative, slope becomes positive. Is important. See, if it is natural log of K versus 1 upon T, K means rate constant, KEQ means equilibrium constant. So equilibrium constant comes when there is a reversible reaction. So whenever there is a reversible reaction, the graph of natural log of K equilibrium versus 1 upon T depends on delta H, LP of the reaction. If it is positive, then graph is same as that of Arrhenius equation. But if it is negative, if it is exothermic, reaction is exothermic, delta H negative, then goes upward. This is the question. For a chemical reaction, time taken for the initial rate of reaction fall to 90% of its value is found to be independent of the initial constant. So tell me, what is the order of the reaction? Time taken for the initial rate of reaction to fall to 90% of its value, it is independent of the initial concentration. Can you tell me what is the order of the reaction? Yes, beta. It is fraction 90%. It is dependent of initial concentration. Time taken for 90% of its value. It is independent. That means it is first order reaction. See, K equal to 1 upon T, natural log of C naught by Ct. This ratio is, it depends upon the ratio. So whenever there is a fraction of the like 50%, it is independent of initial concentration or first order reaction. So it is either 80%, 20%, any fraction. If it is independent of initial concentration, that means it is first order reaction. See, in case of 90%, what is the value? 100 by 10. Not is 100 divided by 90% is complete. So 10. That means, time for 90% is comes out to be natural log of 10 by K. It is independent of initial concentration. It is first order reaction. Keep in mind, whenever it is given that percentage of the, I have the previous lecture I have told you that if it is percentage 10%, 10%, 10%, 100 to 90 and 90 to 81. If it is 10 minutes, here also 10 minutes. So percentage, if it is independent of initial concentration, then it is first order reaction. So for first order reaction, let us say reactant to a product, the reaction follows first order kinetics. Initial concentration A, after time t it is A minus X. You know, Kt is equal to A naught e raised to power minus Kt. That implies A minus X is equal to A into e raised to power minus Kt. So fraction reacted, that is X, is equal to A minus Kt. That implies A common 1 minus e raised to power minus Kt. For fraction reacted, it should be equal to A into e raised to power minus Kt. This is the amount left after time t. Proportional to, if it is Kt, that is equal to initial concentration in e raised to power minus Kt. That means first option is incorrect. Half-life for the reaction is 5-2. See, value of K is not given, time for 90% completion is not given, so we cannot calculate half-life. But time taken to complete 75% of the reaction is 2 times half-life time of the reaction. Is it true? So yes, because our first order reaction, time taken that we have discussed in the earlier class, previous class, that 100 to 50, 50 to 25, 25 to 12.5 and so on. It is first half life, second half life. After second half life, 75% reaction is completed because it left only 25. For T 50% is T half. For T 75%, it is 2 times T. For first order kinetics, it is true. Now, pre-exponential factor in the Arrhenius equation for this reaction has dimensions of time. See, K equal to A into e raised to power minus A by RT. You know, exponential factor has dimensionless. A has dimensions of K. K and K has same dimension, and K is either per second, per minute, or per year or per hour. That means A has dimensions of not time, inverse of time. This is also not true. That means only C option is correct. Okay. Temperature dependence of the rate constant K for chemical reaction can be expressed in terms of Arrhenius equation, which contains the corresponding activation energy terms. The correct plot of the ratio of the rate constants of different chemical reactions at two temperatures, 300 Kelvin and 400, as a function of their activation kilojoule per mole. Yes, beta. What do you do? First of all, know the expression natural log of K2 by K1 equal to activation energy divided by R into T2 minus T1 divided by T1 into T2. So see, if we plot a graph between natural log of K2 by K1 versus activation energy, see, activation energy divided by natural log of 2. Natural log of 2 is constant, means overall it is natural log of K2 by K1 versus activation energy graph. It should start from origin. That means A option and A option is A and C options are straight rejected, so they are not starting from origin, so there is no intercept. Now we left with B and C. Here it starts from 1.38, starts from 0.6. So take any value. Let us take natural log of K2 by K1 as 0.69 is equal to activation energy divided by R. T2 minus T1 is 100 divided by 300 into 400, and activation energy is taken in kilojoule per mole. What is the value of activation energy? And activation energy divided by natural log of 2 we have to calculate. If activation energy divided by natural log of 2 comes out to be 10, that means D option is correct. If it is not correct, obviously there is no need to calculate further. It is option B. So natural activation energy divided by natural log of 2 equal to 0.69 into 300 into 400 into 8.314 into 10 raised to power minus 3 divided by 100 into natural log of 2 is the value, and natural log of 2, you know, it is 0.693 and take it as 0.69 so that we can cut 0.69. What is the value? 4 3s are 12. 12 8s are 96, means almost 10 comes out to 10. That means so D option is correct, because if it is 1.38, it is double. Value comes out to be 20. I hope this one is correct. Have you calculated? Oh, that's part. Okay, what is the, find out the value of K at T infinity. Because K is equal to A into e raised to power minus EA by RT. As T tends to infinity, this part becomes e raised to power 0, 1. K is equal to A. Collision theory, I hope you know that according to this, reactant molecules are assumed to be hard spheres, and reaction is postulated to occur when molecules collide with each other, because as the name suggests, it is collision theory, and number of collisions per second per unit volume is collision frequency, and rate depends upon activation energy as well. Rate is equal to ZAB e raised to power minus a by RT, and this ZAB is collision frequency of the reactants. This is fraction of the molecules with energies equal to or greater than activation energy. If we compare them with Arrhenius equation, ZAB taken as A, then rate of the reaction is equal to rate constant. What are the effective collisions? The collisions in which molecules collide with sufficient kinetic energy and at the same time proper orientation. That is called effective collisions. And that leads to the formation of product. Two factors are there: energy factor, orientation factor. Energy factor, that is activation energy or threshold energy, and orientation is equally important, because if energy is greater than activation energy but molecules are not properly oriented, then that will not lead to the product formation. No product is formed if orientation is improper, even if it meets the energy consideration. Proper orientation is required so that an intermediate is formed and ultimately we get the product. So we modify the collision theory by multiplying it with P, that is the steric factor or probability factor, means the probability of the molecules to have proper orientation. And what is the limitation of collision theory? So main drawback is that molecules to be considered as hard spheres and knows their structural effect. That is the limitation of the collision theory. Catalyst. So catalyst will decrease the activation energy and increase the rate of reaction, and this process is called catalysis. It is not at all consumed, it is recovered at the end of the reaction. Negative catalyst means it will decrease the rate of reaction, and auto catalyst means one of the product formed that act as a catalyst. For example, we have this reaction. Here MnSO formed during the reaction act as a catalyst. This process is called auto catalyst and called auto catalysis. You know, only a small amount of catalyst is required, but catalyst doesn't, this is very important, catalyst does not initiate the reaction, it only fasten the already moving reaction, and a catalyst does not alter even the position of the equilibrium. Magnitude of the equilibrium is not changed by the catalyst, but it fastens the attainment of equilibrium. Time required, it lowers the time needed to attain equilibrium, and catalyst provide an alternate path of lower activation energy. It will lower the activation energy so that rate of reaction is increased, and if it lower means more the difference between these two, greater is the rate of reaction. Yes, beta. Okay. Sorry. Okay, so I will wrap up it here. That potential energy, it will decrease the potential energy. See, if there is a large difference in E and E dash, the rate of reaction is fast. One question is there: potential energy versus progress of the reaction. So which one is the correct option? See, this is the potential energy of the reactant. This one is the potential energy of the product. The potential energy without catalyst is the potential energy by using the catalyst. So L, M, N and O, they represent potential energy of the substrate, transition state in absence of enzyme, N, transition energy of the transition state, the presence of enzyme, and this is the potential energy of the product. And rate of the catalyzed reaction, that increases exponentially the tune of difference between M and N, that I told you now, that if there is a large difference between M and N, the rate of reaction is more. So, and rate of directly proportional to the energy. L and O, energy difference does not change by using the catalyst, it remains same. So only 1 and 2, these options are correct. So that's all for chemical kinetics. Thank you so much. Next session will be of equilibrium, that I let you know when start. Okay then beta. Okay, so thank you guys. There are so many questions. There is no student. It's okay, because I am enjoying teaching. Okay, if someone wish to learn, it's okay. Will not never go waste. I think it's a very good lecture. I have worked so much while selecting these questions. Do share with your friends, to share one who wants to study free of cost.